Okay, today we're talking about the zeros of polynomial functions, and I want you to know in advance that after making the notes and talking to the other teachers and our PLC and the calculus teacher, we are skimming this lesson down, so we'll be able to skip a lot of examples and get the most important parts and what you need to do to carry forward. So, to start off with, we are talking about the difference between rational and irrational zeros. Rational are those that can be written as a ratio of two integers, basically fractions and terminating or repeating decimals. Irrational would be those usually with a radical. We have a theorem called the rational zero theorem that you want to remember, and it basically tells you, oh, this color is better, that the leading coefficient and constant term of a polynomial function with integer coefficients can be used to find the possible rational zeros of a function. All right, let's go see how that works. All right, so we have two examples here. List all the possible rational zeros, okay, and instead of writing that, I'm going to call that PRZ, possible rational zeros of each function, and then determine which, if any, are zeros. So we're only talking about the rational zeros right now, okay? Those that can be written in terms of a fraction. So the first example that we have are those whose leading coefficient is 1. And if the leading coefficient is 1, then all we have to do is worry about our constant term. So my possible rational zeros here are plus or minus the factors of that constant term, which would be plus or minus 1 or 2. And from that point, you take a number and you're going to go use synthetic division. It's only a cubic, so I'm going to go ahead with the number 1. I have 1, 5, -4, -2. And I'm going to go look at whether or not I have a remainder. Because remember we talked about yesterday, if the remainder is 0, then I know it's a factor. So I bring down my 1. I'm going to go through this quickly because we talked about synthetic division yesterday. 1 times 1, 5 plus 1, 6 times 1, -4 and 6, and 2 times 1, so 1 is a 0. All right, and remember, this leaves me with x squared plus 6x plus 2. Okay, the same thing, you can put that in your calculator, you can look at it, but this particular graph doesn't ever intersect the x-axis. So the only zeros that I have from this are 1. Okay, let's look at the next example. We have x to the fourth plus 3x cubed minus 7x squared plus 9x minus 30. Again, my leading coefficient is 1, so I'm looking at my possible rational zeros this time are plus or minus the factors of 30. So we have 1, 2, 3 goes into 30, 4 doesn't, 5 times 6, 3 times 10, 2 times 15, and 30. So those are all my possible rational zeros. And you can imagine that before we had graphing calculators, we had to go through and plug all those in synthetic division and figure out what it was. We had some other tricks to help narrow the possibilities, but now we have graphing utilities available to us. So we're going to look at the graph and the table to narrow our choices down. So to go through this quickly, I went ahead and put the graph in, and this is what it looks like when I put it in the calculator. So you should look at this and see, it looks like we have a 0 right here at 2, and it looks like we might have another one at 1, 2, 3, 4 at -5. Okay, and remember I said we were looking at the graph and the table, so I'm looking at 2 and -5, and if I hit Control T to pull up my table on an Inspire, okay, I can see that 2 gives me 0, and the other one we said was -5, and -5 gives me 0. So I have verified that's where my zeros are, so those are the numbers that I'm going to use for my synthetic division. Let's go highlight that. Uh, oh, here, we'll go with this one. So we had, I think we said 2 and negative 5, and I'm going to put a little positive 2 and negative 5 so I can remember what to start with. Okay, does not matter which one you start with. I'm just going to start with 2. So I put in 1, 3, negative 7, 9, negative 30. Okay, again, should come equal to 0, so if it doesn't, I've made a mistake somewhere. Bring down my 1, 1 times 2, 3 plus 2, 5 times 2, 10 and negative 7, 3 times 2, 9 plus 6, 15 times 2, so it worked out. Now, you will not make any progress if you do not use this depressed polynomial that we talked about yesterday when you do the second zero. So this time when I want to use negative 5, I'm going to use this, the reduced one. This one, remember, is a fourth degree polynomial. This, of course, is a third degree. So I'm always trying to get it down to a quadratic where I can use the quadratic formula or factor. So, and again, this should come to 0. So I bring it down. I have 1 times negative 5, add 0 times negative 5, add negative 5 times 3 is negative 15, so I have 0. And this leaves me with, what is that quadratic? That quadratic is x squared plus 3. Again, no x-intercepts on that graph, so I know that there's no zeros. So to answer our question, which of these rational roots are zeros? We have just verified it algebraically with 2 and negative 5. So that's what you're going to be doing, how you're going to use the table and the graph to look at what to do, but you always have to justify your answer algebraically. Okay, let's look at some examples where our leading coefficient is not equal to 1. And in this case, when you do your possible rational zeros, you're going to take the factors of your constant and put them over the factors of your leading coefficient. So I write my plus or minus. I have the factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. And then the factors of 2, of course, are 1 and 2. So those are the combinations, okay? To actually write those out, I'm going to say my possible rational zeros are all these numbers that I have, because I would put all of those over 1. So I've got 1, 2, 3, 4, 6, 9, 12, 18, 36. And now I got to put them all over 2. So 1 over 2 is going to be 1/2. 2 over 2, 3 over 2, and so really all I need to worry about are the odd ones. 4 over 2 is 2, 6 over 2 is 3, 9 over 2, okay, I didn't write that very well, 9 over 2, 12 over 2 is 6, 18 over 2 is 9, and 36 over 2 is 18. So those are all the possible rational zeros. So I'm going to go back now. I'm going to go to my graph. I got 2x cubed. Remember, I went ahead and put these graphs in there on your calculator. So I'm going to go control to the next graph. And that takes me to our 2x cubed minus 4x squared plus 18x minus 36. This is my graph. Look at my zeros. Okay, so that looks like a 0 of 2. I need to turn off my uh, and if I have a 0 of 2, I'm going to go click on Control T to look at my table. 2 is in fact a 0, so I'm just going to take my table back off. And now I'm going to go back to my equation, and I'm going to start with the number 2. And I have 2, negative 4, 18, negative 36. Again, I need to make sure I should get to 0. Bring down my 2. 2 times 2, negative 4 and 4. 2 times 0, 18 plus 0. 2 times 18, and of course that gives me 0. And this becomes 2x squared plus 18, which, whether you set it equal to 0 and solve or look at the graph, again, no rational zeros. So the zeros that I have to answer the question is just 2. This only have 1. Okay, let's look at 2b. We have our possible rational zeros are plus or minus, and remember, they call this P over Q. If anybody says this, that's what our rational root theorem, they call P the constant and Q the leading coefficient. And so they call them, if you say, hey, what's P over Q? They're taking the factors of the constant term, 1, 3, 7, and 21, and putting them over the factors of the leading coefficient. So again, I'm going to list my possibilities, or my combinations is what it is. Plus or minus everything over 1, 1, 3, 7, and 21, and then 1 over 3. 3 over 3 is 1, 7 over 3, and then 21 over 3 is 7. So these are the ones that I'm going to be looking at. I should have highlighted that back on this graph here. So the one we found from our graph was positive 2. So let's go look at 3x to the 4th minus 18x cubed. All right, and it's not. Let me take off my. It likes to be difficult sometimes. Moving along. There's my 3x to the 4th minus 18x cubed. So it looks like I have one at 1, 2, 3, 4, 5, positive 6, and negative 1. So we're going to go look for positive 6 and negative 1. Okay? Negative 1 is not a 0. And positive 6 is not a 0. So this happens to be one where, unless you zoomed in on your graph, you might not be able to see it. So going back, those were the only choices, and therefore, to answer the question, there are no rational zeros. Okay, these next two concepts, upper and lower bounds, okay, and we are not going to talk about. So we don't have to do those examples because we are now using a graph to simplify our process. We're also not going to talk about Descartes' rule of signs. If you want to know more about it, feel free to come see me. I'll be happy to share it with you. Okay, the last thing we need to talk about is somewhat going backwards, but we've talked about this many times, so it shouldn't be new. When you have a degree of a polynomial, then it has exactly that many zeros. We've discussed this. Fifth degree has 5 zeros. Third degree has 3 zeros. That's what we're going to be working with, and we're going to work with factoring them out and accounting for each of those zeros. Okay? You also have something that you discussed last year in Algebra 2, your conjugate root theorem. What you need to remember is that complex roots, that would be those roots that have I in them, okay? Complex roots always come in pairs. So when you look at this first example, write a polynomial function of the least degree with real coefficients in standard form. We're not going to put it all the way in standard form with the given zeros. They told me that I have negative 3, 1 with a multiplicity of 2, and 4i. So according to my conjugate root theorem, if I have 4i, then I also have negative 4i. So to write my polynomial, f of x equals, remember if it's negative 3, then my factor is the opposite. So it's x plus 3, x minus 1 with the multiplicity of 2 tells me the power is 2 on the factor. And then I have x minus 4i and x plus 4i. Now, we have to have real coefficients, so we can't leave it like that. But standard forms means you would have to multiply it all out. But all I'm going to ask you to do is make sure you don't leave I and don't leave any radicals in your answer. So that gives me x plus 3, x minus 1 quantity squared, and when you multiply that out, you're going to get x squared plus 16. That's that a minus b, a plus b. So I'm fine if you want to leave it like that. Okay, let's look at the next one. We have 2 square roots of 3, negative 2 square roots of 3, 1 plus I, which means we also have 1 minus I. So I might need a little bit more room, so I'm going to start over here. F of x is going to be equal to x minus 2 square roots of 3, x plus 2 square roots of 3, x minus that complex root, and x minus the other complex root. Now, when we simplify this, this is a plus or a minus b, a plus b. So this becomes x squared minus that thing squared. And here I'm going to get rid of the parentheses, leaving me with x minus 1 minus I and x minus 1 plus I. Now, look at this, because those two are the same, and I don't know how that color is going to go on blue. These two are the same. So that is a minus b, a plus b. So when we factor it out, or excuse me, multiply it out, we're going to use the same concept that we did right here. So that leaves me x squared minus, I have to square the 2 and the square root of 3. So that's 2 squared. This is going to be 4 times 3, which is 12. X squared minus 12. And over here, I'm going to have x minus 1 squared minus I squared. And to finish that off, x squared minus 12, we use our pattern, x squared minus 2x plus 1. I squared, of course, is negative 1, so that's minus a negative 1. And that allows us to have x squared minus 12 and x squared minus 2x plus 2. Now you have multiplied it as far as getting rid of any radicals, and making sure you didn't leave I in your answer. Okay, so that's not complete standard form. Standard form would be multiplying the whole thing out, and we're going to stop right here. Okay, 2 more examples that we need to know about. What does it mean for something to be irreducible over the reals? Okay, basically what you're looking at is if it's irreducible over the reals, then you might have a factor like we just saw, x squared plus 4. Okay, that is a quadratic expression that can't be factored with real coefficients. Okay, so when you see one like that, you'll be finished. All right, so we are going to take each of these polynomials and we're going to factor it to find the zeros of the polynomial. So to start off with, I'm going to go graph it and find out what the possible zeros are. Remember, the possible rational zeros are plus or minus the factors of 120 over 1. So I'm going to go to my graph, and I have x to the 4th plus x cubed. So I have to turn this off and on to make sure it works. And control next page. X to the 4th minus x cubed minus 26x squared plus 4x minus 120. So that looks like we have 1, 2, 3, 4, a 0 at 5, and a 0 at negative 6. So we're going to hit Control T to look and see if we had negative 6. We have a 0 at negative 6, and we have a 0 at positive 5. So I'm going to take my table off, and we'll go back. And our possible zeros we said were at negative 6 and positive 5. So we got that from our graph. And now we're going to use that to reduce this quartic polynomial. So again, doesn't matter where you start. I'm starting at negative 6. I have 1, 1, negative 26, 4, and negative 120. All right, again, that should come down to 0. Bring down my 1. I multiply. I add. I'm multiplying, and then I add. I multiply, and then I add, and then I multiply. So that one worked out. Now we're going to use our reduced polynomial or depressed polynomial with the number 5, with that 0, and that again should come to 0. Bring down my first number, multiply, add, multiply, add, multiply, and add. So we're good. And I'm left with, that of course gives me x squared plus 4. So I have linear and irreducible quadratic factors. So to answer this question, the first part is f of x equals x plus 6, x minus 5, and x squared plus 4. That's my linear and my irreducible quadratic. Now they want us to put it in all linear factors. So if they want all linear factors, I'm going to go x plus 6, x minus 5. Linear means I can't have an exponent on that variable directly. So this becomes x plus 2i and x minus 2i. And that is going to answer the next question. So list all of its zeros. So the zeros from that factored form, negative 6, 5, and then plus or minus 2i. How many zeros do we have here? 1, 2, 3, 4, and I have a quartic. So I have accounted for all the zeros that we have. And that's our fundamental theorem of algebra. Okay? All right, I'm going to stop the notes here. I will fill in 7b, so if you want to look at that, you will have another example. And that ends our lesson on zeros of polynomials.